Hello, my name is Arvin Godfrey of BSEC 33, and I'm here to present my Activity 1, which is about blocks of a microprocessor arithmetic logic unit. So, let's proceed. So, our objective was to simulate the basic combinational logic gate equivalent circuit of a 1-bit ALU. So, I separated it into two stages. The first stage, which is about a full adder, pre-multiplexer logic circuit, and the second stage, which consisted of a 4 to 1 multiplexer. So, how did I come up with this? So, let's look at my Proteus 8 Professional, which is a simulator that I used. So, this is the circuit, logic gate equivalent circuit that I managed to come up with to convert the ALU into its constituent parts or logic gates. So, let me indicate it first so that we may see clearly what the different parts are. And as I'm explaining all throughout, as we can see, I have multiple inputs and multiple outputs. So I have input small letter A, input small letter B, representing the operators in the ALU. And I have input A and input B, and input C for the input part of the first stage of the ALU. The first stage consists of an OR gate, an AND gate, and a NOT gate with a full adder circuit. And this full adder circuit was further uh, simplified into the XOR components in the and then OR gates. So as you can see, this is the full adder circuit around here, and this is the stage 1, part of the stage 1. So as we can see, this is the stage 1, which I've successfully converted in the ALU. Now let's look at the stage 2. Now the stage 2 consists of the 4 to 1 multiplexer. So how did I convert it? First, I look at the operators as NOT gates. Then, proceeding to that, the 4 to 1 consisted of 3 AND gates with 3 inputs and 1 output, as opposed to the stage 1, which only had 2 inputs and 1 output. So 3, 3, 3, 3, 1, all throughout, 1 output. And finally, the OR gate, which consisted of 4 inputs and 1 output. So let's put it to the test to see if it is working as intended. So in order to guide me throughout this presentation, I will rely on my PowerPoint presentation, which consists of the table. So let's look at my presentation. As we can see, I've, I've obtained all the tables necessary to make sure that if I did the experiment, that the truth table and the outputs would more or less be the same according to the specifications. So let's first look at the stage 1. So these are the gates that I will be dealing with, the AND gate, the OR gate, and the NOT gate. So let's see, also including the XOR gate. So let's proceed with my presentation of the simulation. So let's run the simulation. So everything is accounted for, no errors. As we can see, the NOT gate sending the opposite. So now, let's look at first the first three gates, the OR gate, the AND gate, and the NOT gate. So when we indicate a 1, so as we can see, for the OR, it's always 1. For the AND, because there's a 0, it will always be 0. Because the input A is connected to the NOT gate, it will always opposite of what the input will be, so 0. So as you can see, that is functioning. So let's look what happens when we add another input. So now the AND gate is now 1. You can also see that there's also a small input here. So later we'll further look in that in depth. So now we've shown that the OR gate, AND gate, and NOT gate are working as intended. So let's go back to the table. Let's look at it again. Let's double check accordingly. So for AND gate, when there's different inputs, only with the same output. Same with the OR gates. Only when there's a 1 or a high, there will always be an 1 output. And for the NOT gate, always opposite the input. So you can see we fulfilled that first part, that first stage. Now let's look at the stage 1.5, the other part of the stage, the full adder circuit. So with the full adder, let's look at the table. As we can see, there's 3 inputs, 2 outputs, sum, and a C out or output C. So as we can see, it's 3 inputs. So let's take an example here. So let's say 0, 1, 0 will result into 1 in the sum and a 0 in the C output. So let's look at that. So let's change the B to 1. So yeah, there we see there's an output. So it works as intended for the first instance. Now let's look at other instances to see if it is really working. So let's look at all the inputs. 1, 1, 1. So as expected, if we have an input of all ones, we should have an output of all ones for the full adder. And as we can see, the full adder is working as intended with the full ones. And again, let's check it again. If we see if this is really working, let's take the last one because as with all experiments, we always need to take three examples. So let's try 101. So there should be a zero in the sum and one in the C output. So let's look at 101. 101. So a zero in the output sum, but there's a one in the output C. So let me realign first. Okay. Uh, Sorry for the minor difficulties. Okay. So here we go. 101, 01. Okay. Working as it did. Now let's go. So as we can see, we've completely or successfully created stage one. We have the stage one, the full adder with the three gates. Now let's move to the stage two, the much more difficult stage. How will we determine if this 4 to 1 multiplexer converted into its logic gate circuits is correct? So as we can see, there's input A, input B. Let's look at the table. Let's look at how it will be guided by it. So as we can see, oh, the 4 to 1 multiplexer truth table is rather simple. For the operators, you will be using the operator, so we will be manipulating the operator inputs. And the output will be depending on whether on the values of the inputs such as x0, x1, or a, b, c, d, a to d will depend on the operators and the input. So the value of m or output q will be based on what the inputs will be from a to d, x0 to x3, and accordingly to what the operators conditions are. So these are our conditions 0, 0, 0, 1, 0, 1, 1 because this is few. Let's test it out. So okay. So let's look at 0, 0, and 1, 1 for a quick presentation. So when it's 0, 0, it should be x0. The value of q or m should be x0. And for 1, 1, the value of m or q should be x3. So let's try that out. So it's 0, 0. What's the value of x0? 0. So the value of q, 0. So that's one. That's correct. So let's look at 1, 1. So what is required when it's 1, 1? So it should be the final value x3. So let's look at it. So 1, 1. Yes, yes. And 0, 0. So what's the value of x3? Because when you look at it, output x0, x1, x2. So where's x3? There's x3 output sum. As, with our earlier presentation, of our professor, he showed us that the sum is the x3. So as we can see, 1, 1, 0, 0. Now let's try 1, 0. So what should be the value when a is 1 and b is 0? Small a 1, small b 0. So let's look at it. 1, 0, 0, 1. So it's either x1 or x2. So let's look at the value to find out which one is it. So as we can see, when it's 1, 0, the value is 0. So which one are we looking at? Is it x1 or x2? So as we can see, the value earlier was from x1. So we can say that C0 is input small letter a. So if we reverse that, now we see the value is x2. It's 1, 1. So even if we try to manipulate the values in such a sense, as we can see, when out b is 1 and input a is 0, it will only focus on output x2 from the NOT gate. So if we try to manipulate the NOT gate, as you can see, the output q is changing. No matter the different changes here, here, and here, it will only focus on the x2 value. Even if we add even more, nothing will happen. Even if we add another input, nothing will change. It will always focus on the output x2. So from there, we can see that our multiplexer is working. Again, as with all experiments, we need 3 more examples to focus on. So let's focus on one. So again, this one is focused on x1. So let's manipulate the value of x1 to change. So again, no change. There's a change. Again, let's manipulate even more. So there's a change. There's a change in output, some, but there's no change. So it's focused on x1. So let's try to remove x0. So again, because it's an AND gate, we cannot manipulate in a sense that OR will be 0. So that cannot be even this cannot be 0 and this be 1. So that's a different condition. So again, for the final experiment, so 1, 1, which is focused on the sum. So as long as the sum is 0, it will not change. So let's put it, okay, it's 1, 1, let's change this. Let's manipulate, okay, when we change that, it becomes 0, so isolate. So again, it's only focused on the output sum as well. Okay, so yeah. So from there, we managed to verify that our 4 to 1 is working, as will the stage 1. So the stage 1 and the stage 2 are working accordingly with the use of our logic probes to determine which ones are to determine the input states and the output states. We could say we've successfully identified the stage 1 and the stage 2. We've successfully created equivalent for them, and it's working as intended. So let me stop the simulation. So let's go back to my objectives. What were my objectives? To simulate the basic. So I managed to simulate the ALU by first creating the full adder pre-multiplexer logic circuit, which is working, and the second stage, which was the 4 to 1 multiplexer, which was also working in tandem with the stage 1. So from there, we managed to verify the truth table, the full adder truth table, and the 4 to 1 MUX truth table. So from there, I would like to thank you, and these are my references for the images that I've used in the earlier slides. And God bless to all those who are listening. Have a nice day.